Okay, we have this national bakery and they want product consistency like McDonald's has, right? When you buy a Big Mac from McDonald's in New York City, it tastes the same as it does in Hawaii, Idaho. So companies, international companies, national companies want that consistency. When you have regional bakeries or local bakeries, their recipes are going to be different from local bakery. But a national company like Burger King, McDonald's, Dunkin' Donuts, they want this consistency. And the way we measure consistency is with standard deviation. So if the standard deviation is, if your product is consistent and has the same taste, the same texture, you're going to have a very low standard deviation. If the donuts one day are huge, the next day they're small, or in this case, if too much custard is squirted into the inside of a Boston cream donut, some days it'll have too much custard, other days it will have too little. The people that like lots of custard will be happy when it has too much custard. The people who like more donut, less custard, they're not going to be as happy, and vice versa if there's too little. So you want to have this consistency. And one way to understand whether you do or not is you can do a test involving the standard deviation. And in this one, a Boston cream has chocolate frosting on top. It's got on top of a donut without a hole. And then you put a needle inside of the donut and you squirt a bunch of custard in it, right? And the tested recipe that most people love, in this particular case, calls for a half of custard filling. And this company randomly samples its bakeries, and the data show at the bottom, to keep its costs low, because custard is more expensive, the company wants to test to see if the standard deviation of custard filling per donut exceeds 0.05 ounces. The recipe calls for a half ounce of custard, right? Is every donut going to have a half ounce in it, Jana?
No.
It's not, right? It's impossible to have every donut have exactly to 5 decimal places a half ounce of custard. It's going to vary from donut to donut, especially if you're doing it by hand. If you're doing it with robots, it's going to be easier to keep the ounces as close to 0.5 ounces as possible, right? So we could do a one mean test here on whether the average is 0.5 ounces, right? And an average, that test could be positive, indicating that, yeah, it looks like a half ounce is in each donut, but one donut might have 0.6 ounces, and the next donut might have 0.4 ounces. The next one might have 0.7 ounces. And then the fourth one would have 0.3 ounces. That averages to 0.5. So you don't want to just test the mean, which we could do here. You also want to test the standard deviation. So you want, instead of having 0.5, 0.7, 0.6, 0.4, 0.3, which averages to 0.5, you want something more like 0.51, 0.49, 0.48, 0.52. You want that instead of 0.7, 0.3, 0.4, 0.2, 0.5, right? So you can test for the mean, which this company does, and you can also test for the standard deviation. Okay, so that statement there, the standard deviation of custard filling per donut exceeds 0.05 ounces. What statement is that? Which of these is true, do you think?
Alternative?
It's the alternative, and why? Why is it the alternative?
Because it's different than like 0 staying the same.
Well, the alternative never involves the word equals. If it said is at least 0.05 ounces, then it'd be the null hypothesis, because at least includes the word equals, right? At least is greater than or equal to. Exceeds is greater than. So the null hypothesis, spelled with two L's right here, right? If you rotate those two L's, 90-degree angles, it's an equal sign, right? It's an equal sign. So the null involves the equal sign. That's how you tell. The null can be sigma squared is equal to 0.05. The null can be sigma squared is less than or equal to 0.05, or sigma squared is greater than or equal to 0.05. All three of those would be the null hypothesis. The alternative is going to be less than 0.05, greater than 0.05, or not equal to 0.05. Not equal to is less than or equal to, right? Or sorry, less than or greater than. So the alternative hypothesis never includes equals. In a graphical version of this, in this particular case, with the null hypothesis being less than or equal to, that would be the normal distribution, the lower tail of the normal distribution plus the hump of the distribution. The hump of the distribution is equal to, the lower tail is less than because it's pointing left. The alternative hypothesis involves the upper tail of a normal distribution, or in this case, a chi-square distribution. So the equal sign graphically is the hump of the distribution, the less than is the left tail, and the greater than is the right tail. That's how the null and the alternative hypothesis split the test statistics distribution in three, right? So this one is alternative, like you said, right? And then what is the hypothesized value of the null? If this is the alternative hypothesis statement, right? And we want to test this number, we're going to compare our standard deviation to that number. What number do we put into that box there? Jana?
Oh, is it 0.25? I tried 0.05 and it didn't work.
Yeah, it's not point.
No, it's not that.
This right here, standard deviation.
Yeah.
That is that right there. The standard deviation is sigma.
Mm-hmm.
Right? And we're testing for sigma squared. So you have to actually square 0.05.
Oh, so 0.0. I just did that was silly. 0.0025.
Yeah, 0.0025, exactly. And we get it right if we check it right. And then this is, of course, 0.0025 as well, right? Okay, and then what kind of test is this? The way you determine what kind of test this is you look at the alternative hypothesis. Is that pointing to the upper tail of the distribution, or is it pointing to the lower tail of the distribution?
It's upper tail?
Yeah, so it's an upper tail test. That's important to identify because if it was less than or greater than, it would be a two-tail test. Another way of saying that would be not equal to, right? It'd be pointing to the lower tail and the upper tail. It'd be a two-tail test. If that's the case, then you have to divide the significance level by 2. But because it's an upper tail, it's a one tail, and this one tail test happens to be an upper tail, you divide the significance level by 1, right? So knowing that determines how you're going to affect that significance level. And we're going to leave it alone by dividing by 1, okay? Because it's a one tail test. Now we have to copy our data in. Let's grab the data. I'm going to grab the label and the numbers and the letter S in submit. So I can copy it and maintain the table structure from HTML into Excel. Hey, that rhymes. That's the first time I said that. The tireder I am, the better I am at rhyming. Yeah, we want to maintain the table structure from HTML to Excel, you know. I know, I'm a nerd.
It was good. It was good.
It's good, right? I like to make everything look nice and symmetrical. Okay, now what I'm gonna do is I'm gonna copy this stuff into Excel. I'm gonna put the sample size in C2. Oh, let me do this. There's an HTML table underlying this, so I'm going to copy the sample size down to the A. I'm going to put sample size in A1. There we go. Okay, so my sample size, how do you keep the sample size, Dana?
Equals count and then highlight the numbers.
Count. And then I'll show you something real quick too before we do that. I can name the numbers. So if you highlight A2 down to 51, where's your last number at? Is your last number at 51?
Mine's at 41.
Okay, so I'm going to highlight everything from my first number to my last number. And then I'm going to come up here to this box. I'm going to give it a name. I'm going to call it billing. That'll make it easier to do the analysis. So I've named cells A2. I've named cells A2 down to A51. I've given them a name. So these cells in this rectangle here is what's called an Excel object. And I've named that object billing. Okay. Now, why did I do that? Because it's going to make this over here easier. I didn't do this in class on Wednesday. I'm going to type billing. See that? And then it highlights everything in that object. So this is a really good introduction to like Python. In Python, you don't see the data, you just see the code line, right? You can print in the output what the data looks like, but in Python you don't see it. So that's why when I teach Python, I teach it parallel with Excel. I show students how to do it in Excel first, and then we do it in Python, and it makes it easier because I think most students are visual learners. So count, I got 50, right? What about the variance? How do I get the variance? I can start typing VAR, right? I can start spelling variance. I stop at VAR and I got a choice between P and S. Which one is it going to be, P or S? This was in the video yesterday that you watched yesterday, by the way. I think Emmanuel asked why there's a difference, and I went through a little explanation that you didn't see because the whiteboard wasn't captured. But which one are you going to do? Are you going to do P or .S?
S for the sample?
S for sample, right? You're going to do S for sample. And then all you got to do is type billing. Notice when you start typing billing, you can just double click on it, right? This right here, this icon, this table with two blue dots in it, or two highlighted cells, that's the icon for object. F of X in a circle is the icon that indicates it's a function in Excel. I'm not sure if you knew that. And then for degrees of freedom, do I type equal degrees of freedom?
Can't you just do the sample size -1?
Yeah, exactly. I was trying to get you on that one. Yeah, just 50 minus 1. In my case, 51. D2 minus 1. And then we got to do the chi-square statistic. Because this is kind of like a review class, we're supposed to remember what those are, right? So like I did in class yesterday, I just grabbed a image from the internet. Let's go images. There's the chi-square test statistic. This is the Greek letter chi. When people see how it's spelled, they always say chi-square. And I always respond with, it's not chai tea latte from Starbucks, it's chi-square, a test statistic in statistics. Okay, so this is what the chi-square distribution looks like right here. The thing about the chi-square distribution is the values are all positive. See that? From 0 to infinity. So chi-square starts at 0. The height is 0 at 0. Unlike the t-distribution or the standard normal distribution, the left tail, all the way to the left, that's 0, not negative infinity. And the reason why that is because can a number squared be negative?
No.
No, these two numbers have to be positive. S by itself can't be negative. S by itself, when you calculate S, it can't be negative. Because it involves squaring differences, summing squared differences, right? And then divide by a positive number. And if n, can you have a sample size of 0?
No.
Nope. You have to have, if you have 0 sample size, you didn't sample the population. If you randomly sample the population once, then your sample size is once, right? And that's not a very good way to approach decision making in business, right? So you want your sample size to be bigger than 1. So this number is going to be positive. These numbers are going to be positive. And notice this chi-square, the way it looks, it kind of looks like a T on its side. So the way you kind of think of what chi-square is, it's just kind of a squared T distribution, if you will, right? Intuitively, it's like you square the T distribution. And when you square the T distribution, you get something that exists in positive number space, right? Now, the thing about this is the reason why it looks like this hump here, the hump of the distribution, is at approximately n-1. And the reason why that is because if the equal part of the null hypothesis is true, what do we expect S squared divided by sigma squared to be equal to? What do we expect that to be equal to? If the equal part of the null hypothesis is true, what do we expect that to be equal to?
Can you say that again? I'm sorry.
If the null hypothesis, the equal part of the null hypothesis is true, if sigma squared equals some hypothesized value, right? What do we expect that ratio to be?
1 to 1.
We expect their difference to be 0, right? Which is why the T distribution is at 0. We expect their difference to be 0. We expect their ratio to be equal to 1. You see that? So if the null hypothesis is true and our sampling is accurate and our sample size is sufficient, we expect these two things to be equal and their ratio is 1. Now, what is 1 times n-1? What is 1 times n-1?
n-1.
Yeah. So if the null hypothesis is actually true, and we'll never know that, and our sample size is random, representative, and large enough, then we expect S squared divided by sigma squared to be equal to 1. 1 times n-1 is n-1. So we're expecting chi-square to be n-1, which is why the hump is at n-1. You see that? The n-1 kind of is where the hump is, right? It's equivalent to the 0 in the T distribution, right? If the difference is insignificant, the t-statistic will be in the hump close to 0, right? If the difference in these two is 0, right? The test statistic will be in the hump of the distribution near n-1. Does that make sense?
Yes.
Okay, cool. All right. So when you do the hypothesis test, we're using the S squared as an estimate for sigma squared. And this value down here is our hypothesized value, right? This is our hypothesized value. This is our estimate of sigma squared, right? So let's go back to our problem here. I love teaching this stuff because I like focusing on the intuition. Okay, so our n-1 is 49, right? That's our degrees of freedom. So that's the first part of the sigma squared, right, Gina?
Yep.
That's the n-1 there, right? Okay, and then we got to multiply that by our estimate. We're going to multiply that by our estimate of the population variance, sigma squared. We only have the sample variance. We don't have the actual variance, right? And we're going to divide that by what? What are we going to divide that by? We're going to divide that by our hypothesized value. Right?
Yep.
We want the custard to be as close as possible to 0.05 ounces, right? Sorry, 0.5 ounces. And we concluded that if our standard deviation is 0.05 ounces, people who like lots of custard and people who don't like lots of custard, they can't tell the difference in a low custard donut versus a donut with lots of custard in it, right? So
Yep.
0.05 is small enough where discriminating taste buds can't tell when the custard is on the low end and when the custard is on the high end. If the standard deviation was 0.5, they'd be able to differentiate, right? It's kind of like Pepsi and Coke. I don't really taste the difference between Pepsi and Coke. My grandpa could differentiate the two. I didn't believe him until I did a taste test with him one night. I actually taste tested my grandpa on Pepsi and Coca-Cola when I was in my 20s, and I was living with them and going to college. All right, so is my chi-square statistic close to my degrees of freedom? Are they pretty close?
Yeah, they're pretty close.
Yeah, they're pretty close in relative terms, right? In difference, they're 10 apart, right? But 10 divided by 49, right? 10 divided by 50, that's relatively pretty close, right? So this would be like the test statistic in a one mean test being like 0.9 or negative 0.8. They're kind of close to 0, right? What's your chi-square statistic equal to?
Mine's really far off. My chi-square statistic is 79.1325, and my degree of freedom is 39.
So we're kind of thinking you're out there in the tail, right?
Mhm.
You're out there in the tail on the right, right? So
Yep.
your variance, like my variance, is bigger. My variance is 0.0031. It's bigger than 0.0025. And so your variance is relatively larger than mine, right? Compared to 0.0025. So maybe on Monday, my filling ounces is Monday's results. Yours is the results on Tuesday, right? So if that variance is too big, we may not want to ship your donuts, right? Because it might upset our customers. They might say, man, these go from donut to donut, they taste it. Now, how do we get the p-value here? What kind of test statistic is this? I'm gonna go back up here and put in sample variance. Okay, we have the sample size, sample variance. We have a chi-square test statistic that uses the sample variance to find out if the ratio is too large or the ratio is too low, right? Now we got to find the p-value. The p-value is chi-square, right? Which one do you think we want to use here? We have chi-square. when we were doing t-distribution, we did t dot dis to get the p-values, right? But we have this additional one. We got chi-square dot dis, and we got chi-square dot dis dot rt. What do you think the RT stands for? And it's not, oh, that's RJ. RJ is the raccoon and Over the Hedge, sorry. My kids watch that all the time. Over the Hedge, it's one of the funniest kid movies out there. You know, animated kid movies. It's like Shrek. It's that good. Yeah, so do you want to use dot RT or you want to just use the first one?
RT,
Why do you want to use RT?
right-tailed?
Right tail, right? And this is a right tail test, right? A right tail test is an upper tail test, right? So let's do that. And then the X value is just the chi-square statistic. And then the degrees of freedom, that's it. And our my p-value is quite large, right? My p-value, having a large p-value like this, pushes the chi-square statistic into the hump area of the distribution, right? What's your p-value?
0.0002.
0.002?
0002.
Oh, 3 zeros.
Yep.
Your p-value is really small, which means the chi-square stat is way out in the tail, right? So you have a big test statistic because your p-value is small. Your test statistic is big, which means the difference between the sample variance and what you want the variance to be is big, right? My chi-square statistic is small, which means my p-value is big. And when your chi-square statistic is close to your degrees of freedom, like mine is, your p-value will be big, and you're in the hump area of the distribution, which means the ratio, if my chi-square statistic was 49, right? If it was 49, then my sample variance would be equal to my 0.0025, right? So the closer this gets to the degrees of freedom, the closer the ratio of sample variance over what we want it to be is equal to 1. So the closer this is to the degrees of freedom, the closer my sample variance is to value we want it to be, right? As this gets larger and larger and larger, as it gets bigger and bigger and bigger, like in your case, as it gets bigger and bigger and bigger, that sample variance is getting a lot larger compared to what we want it to be, right? So let's just pop these numbers in. Hit enter. It looks like we get everything right. Now, if we had chosen to do this instead, we'll calculate the p-value a different way. Instead of using .rt, I'm going to use .dis. And I have to add one thing to this. I have to add true. I don't understand why Excel uses true. When you do this in Google Sheets, it doesn't ask you for true false. But when I do this, what do I get? I don't get the probability of the left tail. What do I get? If I add those two together, I get 1, right, Gina?
Yep.
Yeah. So the one I calculated here is the left tail probability. This one right here is the right tail probability. Right tail. And this is the left tail. So this is the Beyonce probability to the left, And this is the Sasha Fierce probability her stage presence to the right. See that? Okay. Now, my significance level is 5%, right? If I change this to percentages, if I change this to a percent, I get 13.67%, right? My p-value is bigger than my significance value, right? So that means the difference, because I'm inside the hump of the distribution, my test statistic is inside the hump area of the distribution. The difference between my sample variance and what I want it to be is insignificant. So I have evidence in support of the null. Because this right here means hump of the distribution. This is the little left tail. This is the hump. So these two together are the hump and the left tail of the distribution. This is the upper tail of the distribution. So my p-value pushes my chi-square statistic inside the hump. So I'm thinking the equal part. I'm thinking the equal part of the null hypothesis is true, right? I have evidence in support of the equal part of the null hypothesis being true. So I have evidence in support of the null, right? Do I accept the null? I can't accept the null, right? But I can't, instead of accepting null, I can think accept. But instead of saying accept, which I'd be ridiculed by statisticians throughout the world, I can think accept, but then I have to come up with a synonym for it. And that synonym is cannot reject the null, right? Now, Jana, your p-value is tiny, right?
Yeah.
Your p-value is 0.2%, right?
Mm-hmm.
And your significance level is at 5% in your problem?
Yes. Yep.
Okay, your p-value is small, which means your chi-square stat is big, which means your sample variance is big relative to what we want it to be. So what are you going to conclude?
I reject the null.
You're gonna reject the null, right? So are you going to ship those donuts?
Say that again, I'm sorry.
Are you going to ship the donuts that have a high variance of custard?
Yes.
Are you going to ship them?
Oh, no.
Right. So what you may do instead is you may sell that group of donuts as a knockoff brand, right? Have you ever walked in a grocery store and seen the green label, the store brand vegetables and the branded vegetables, like what do you got? Green Giant. You got the Green Giant brand and you got the Walmart brand. Have you seen that?
Yep.
Yeah, when you go shopping, you see different brands of vegetables, for example, like canned vegetables. What you may do is you're not going to throw those donuts away. You might just sell them to, you might sell them as a cheaper brand. You might have two versions of the brand, right? You might have your premium brand, and then you have, or you might supply them to somebody who puts their brand name on them.